Hi, today we're going to be looking at 7.6, solving quadratic trigonometric equations. The goal of today's lesson is to solve quadratic trigonometric equations using graphs and algebra. This will allow us to use trigonometry to solve real-world problems involving sinusoidal functions. So let's take a look at the first example. First of all, please recall special triangles and radians, the pi by 6, pi by 3 triangle and the pi by 4 special triangle. Recall the cast rule and, of course, the Pythagorean identity sine squared theta plus cos squared theta equals 1. So let's take a look at this first example here, where we want to solve sine x plus sine 2x equals 0 on the interval from 0 to 2 pi exactly. Okay, so first we'll do a little bit of algebraic rearrangement and cleaning up here. So we see that we've got sine x and sine 2x. We need to rearrange or change this because this is a single angle and this is a double angle. So we can't have single angles and double angles combined in one problem. So we need to rewrite this into a handy formula that we already know, so that we're just dealing with single angles. What would sine 2x be written as? So we can say sine x plus 2 sine x cos x equals 0. That's the double angle formula for sine. And now from here what we can do is we can take these two terms and we can factor out what's common. So now we've got one factor, sine x, and another factor, 1 plus 2 cos x. And when you multiply these two factors together, we get 0. So when you multiply two factors together that gives you 0, either one of the factors equals 0, or the other equals 0, or both. So we can say sine x equals 0, or 1 plus 2 cos x equals 0. This one's pretty easy, we can just leave that as it is. And this one just need to rearrange there and solve for cos x. So we subtract 1 from both sides. Then we divide both sides by 2. And then what we need to do is we need to analyze these things. Okay, so we've got cos x equals negative a half. And we know that the angle x is between 0 to 2 pi. We need to place the terminal arm somewhere on the Cartesian plane using that negative sign to guide us. So keep in mind the cast rule. Where would a terminal arm land if the cosine is negative? Okay, that's correct. That would be in the second and third quadrants. So here is x1, here is x2, and this of course is our related acute angle beta, and this is also the related acute angle beta. So now we look at cosine of beta equals 1/2, and from the special triangles we see that beta would be pi by 3. So now if beta is pi by 3, then that means x1 is pi minus beta, which is 2 pi by 3, and x2 is pi plus beta, which is 4 pi by 3. Okay, and then now if we look at sine x equals 0, we've got so just going back here, we've got two values of x that if we were to sub that into this original formula, we would get 0 if we plugged in 2 pi by 3 and 4 pi by 3 into this and solve that. Now we're going to look at sine x. Where is sine x 0? Well, in this case, these special angles, special triangles won't help us too much, but what we can do then is we can look at the sine curve. And I'll just draw a quick little sketch of the sine curve here. From 0 to 2 pi. And we see that sine x is 0 at 0 radians, pi radians, and 2 pi radians. So therefore x is 0, pi radians, and 2 pi radians. So therefore the final solution would be that x equals 0 radians, pi radians, 2 pi radians, 2 pi by 3 radians, and 4 pi by 3 radians to solve this quadratic trigonometric equation here. Okay, let's continue. Now we've got cos squared theta plus 2 sine theta minus 2 equals 0, and we're trying to solve this as theta is between 0 and 2 pi. Notice that we've got a mixture of cosine and sine. So a mixture like that will be very difficult to work with. So think of formulas that use this, that we could rewrite that in terms of sine. If we think of the Pythagorean identity, sine squared theta plus cos squared theta equals 1, which is found at the top of your paper, I'll just write that again here. We realize that we have cos squared theta here. If we were to rewrite this in terms of cos squared theta, we get 1 minus sine squared theta. So if we were to substitute this in for cos squared theta in the equation, then the equation is completely in terms of sine theta. Okay, so let's substitute that in. So we got 1 minus sine squared theta plus 2 sine theta minus 2 equals 0, and I'll put this in brackets just to identify that that came from the substitution over here. And then we'll just simplify this a little bit. So we got negative sine squared theta plus 2 sine theta minus 1 equals 0, because I added 1 to negative 2 to get negative 1 here. Then I'll multiply through by negative 1 just to clear out that negative from the front. So we get sine squared theta minus 2 sine theta plus 1 equals 0. And we can see that this is a perfect square, the plus 1. The sine squared is a perfect square. And if we see what two numbers would multiply together to give you positive 1, well, we've got two choices, either positive 1 or negative 1. And if it was positive 1, then we get plus 2 sine theta, so it can't be that. So it must be negative 1, so we get negative 2 sine theta there. So this is a perfect square trinomial, so we can rewrite this as sine theta minus 1 all squared. Take the square root of both sides, and then add 1 to both sides, so we get sine theta equals 1. So then if we were to then look at the sine curve again, sine theta equals 1 at exactly one spot when we're looking at the range, or the domain, sorry, between 0 and 2 pi, and that is when theta equals pi by 2. So therefore, theta equals pi by 2.